There is a galaxy near the edge of observable time that contains oxygen. You can feel what that means before you can explain it. Oxygen takes at least 1 billion years to forge inside dying stars. This galaxy is 290 million years old. In 2024, the Scuola Normale Superiore in Pisa confirmed it through direct spectroscopic measurement, not an estimate, a detection. The galaxy should not exist. It is not alone. The universe's own expansion rate now gives two verified, incompatible answers. Light is arriving from behind fog that should have swallowed it forever. Hundreds of objects in the early cosmos have defeated 4 successive explanations. For 30 years, cosmologists believed the map was nearly complete. On Christmas morning, 2021, a telescope launched that could read the light no other instrument could reach. What it has sent home is quietly dismantling the most successful scientific framework in history. We will trace the discoveries, confront the crisis they have opened, and follow the scientists who cannot look away. If that pulls at you, subscribe. We are only at the beginning. 13.8 billion years of cosmic history. And the most important chapter may be the one we got wrong. Inside the nose cone of an Ariane 5 rocket, sitting on a launch pad carved out of jungle on the northeastern coast of South America, there was something that did not look like a telescope. It looked like a folded thing. 18 mirrored hexagons hinged inward against 2 side panels. The whole structure collapsed into a shape compact enough to fit inside a cylinder 4.5 meters across. 6.5 meters of mirror, folded. A sunshield the size of a tennis court, folded. The most complex scientific instrument ever sent to space, folded. Because there was no other way to get it there, and no second chance if the unfolding went wrong. It was Christmas morning, 2021, 7:20 in the morning, Eastern Time. In control rooms in Baltimore and Paris and across Europe, engineers sat with their hands in their laps and their eyes on screens. There were no crowds in the street. There was no countdown cheer. The people who understood what was at stake were too frightened to celebrate. They had spent years running through every possible failure, every bolt that could shear, every motor that could jam, every hinge that could stop 3 degrees short of its target and lock there permanently because there was no mechanism to try again. They had counted the single points of failure, 344 of them. 344 individual mechanical actions that had to occur in the correct sequence, in the correct order, in the cold and the dark, and the silence of space, without any human hand to help. Any one of them failing could end the mission entirely. There would be no shuttle to fly up and fix it. The telescope was heading somewhere no repair crew had ever gone and could not follow. The rocket lifted. The Ariane 5 performed perfectly. 27 minutes after launch, the telescope separated from the upper stage. 30 minutes in, the solar panels deployed and power flowed. The telescope was alive. But alive and operational were 2 entirely different things, and the engineers knew it. The harder part had not yet begun. To understand why the deployment was so terrifying, you have to understand what the telescope is made of and why every single design choice was forced on the engineers by physics itself. Start with the mirror. 6.5 meters across, roughly the width of a large living room. 18 individual hexagonal segments, each one shaped from beryllium, a metal chosen because it is both lightweight and extraordinarily stable when exposed to extreme cold. Each segment was then coated in gold, a microscopically thin layer, chosen because gold reflects infrared light better than almost any other material known. Assembled together, those 18 segments form one of the most precisely shaped optical surfaces ever manufactured by human hands, with tolerances measured in nanometers, billionths of a meter. Now the problem. A mirror 6.5 meters wide cannot fit inside a rocket fairing. The Ariane 5's payload fairing was 4.5 meters across. The mirror is simply too large, and so the engineers designed the mirror to fold, a central core flanked by 2 side panels that hinge inward like wings tucking against a bird's body. The whole structure collapses into something compact enough to survive launch, then must unfold in space and lock into permanent alignment. Nothing like it had ever been attempted at this scale. The sun shield presented a different kind of problem entirely. To observe in the infrared, a telescope must be extraordinarily cold. The infrared wavelengths the telescope was built to detect carry heat, and any warmth radiating from the telescope's own structure, or from the Earth, or the Sun, or even the Moon, would contaminate the signal completely. The instruments needed to operate at around -230 degrees Celsius, colder than the frozen vacuum between most stars. To get there, the telescope needed to be shielded from every heat source simultaneously. The solution was a 5-layer thermal barrier, roughly 14 meters long and 21 meters wide, made of a material called kapton, each layer aluminized to reflect heat. Think of it as the world's most sophisticated space blanket, the size of a tennis court and as thin as a human hair. On the side facing the sun, the shield absorbs enormous heat. On the telescope side, the temperature drops to nearly nothing. The gradient across just a few feet of layered film spans hundreds of degrees. Even that was not cold enough for one of the telescope's 4 instruments. The mid-infrared instrument, the one designed to detect the longest wavelengths and therefore the oldest, most stretched out light in the universe, required active cooling. A cryogenic refrigeration system built into the spacecraft, pushing its detectors down to around -266 degrees Celsius, approaching within 7 degrees of absolute zero. It is one of the most sophisticated cryogenic systems ever sent to space. All of this, the mirror, the sun shield, the cooling system, was designed for one purpose: infrared light, the light that the universe's oldest, most distant objects emit. When the first galaxies formed, they released light at visible and ultraviolet wavelengths. But in the 13+ billion years since then, the universe has been expanding, and as it expanded, it stretched those light waves with it, pulling them from visible wavelengths into the infrared. By the time that ancient light reaches us, it is invisible to human eyes. Every camera ever built, every optical telescope that has ever looked at the sky, cannot see it. This telescope was built specifically to receive it. That is what was folded inside the rocket on Christmas morning. A machine designed to catch messages sent before the Earth existed. The deployment sequence began immediately. No pause, no celebration. Within days of launch, the sun shield began to unfurl. That enormous gossamer structure folded into a compact stack for the ascent, now pulling out, tensioning, separating into its 5 distinct layers. Each one had to stretch across a frame the size of a tennis court. The operation involved hundreds of individual motor steps, cables reeling in, booms extending, membranes pulling flat. Any snag, any tangle, any motor drawing too much current could crumple the shield into useless wreckage. For 5 days, the team watched the shield deploy one increment at a time. It worked. The layers separated, the shield tensioned. The cold side of the telescope began to cool. Next came the secondary mirror, swinging out from its folded position on 3 thin support struts and locking into alignment. Then, on the 7th and 8th of January 2022, the 2 side panels of the primary mirror hinged outward from their folded position. Each hinge had to rotate to the exact correct angle and then lock permanently, because there was no mechanism to rehinge them if they stopped short. Controllers in Baltimore called out each latch as it engaged. The room had been holding its breath for nearly 2 weeks, but the telescope was still not ready. 18 mirror segments, now extended, were each slightly misaligned, launched that way on purpose, because precision alignment cannot survive the vibration of a rocket. Each of the 18 segments had to be individually adjusted using small actuators on its back, nudged by fractions of a millionth of an inch until 18 separate reflections of a distant star collapsed into one sharp unified image. The alignment target was a bright star designated HD 84406 in the constellation Ursa Major. Over weeks of careful remote adjustment, 18 ghost images of that star slowly, painstakingly converged. On the 16th of March, 2022, the alignment check came back clean. 18 segments were one mirror. The precision achieved was comparable to adjusting a reflective surface until it could detect the warmth of a single candle flame from the distance between Washington and Los Angeles. The telescope was parked approximately 1.5 million kilometers from Earth, on the far side from the Sun, at the gravitational equilibrium point, where the combined pull of the Earth and Sun can hold a spacecraft in a stable orbit without constant fuel expenditure. Cold, still, aimed at the oldest darkness in existence. The engineers had done everything that human beings could do to make this instrument work. Now it would turn its gold mirror toward the sky, and whatever it found there, it would find on its own. Before it looked, there was a picture of the universe that nearly every working cosmologist believed was essentially correct. A model tested against every observation for decades. A framework so precisely calibrated that some researchers had begun to wonder whether the great open questions of cosmology might be answered within their lifetimes. That was the world the telescope inherited when it opened its eyes. There is a particular kind of confidence that comes not from certainty, but from accumulation. Not the confidence of a person who has never been wrong, but of someone who has been tested repeatedly, from every direction, over many decades, and has not broken yet. That was where cosmology stood in the years before the telescope opened its eyes. Not arrogant, not incautious. Simply the confidence of a field that had done the work, checked the answers, and watched them hold. The framework underpinning that confidence had a name: lambda cold dark matter. It described the universe as a system composed of 3 ingredients in precise proportions. 5% of everything that exists is ordinary matter: atoms, molecules, the substance of stars and planets and oceans, and everything you have ever seen or touched. 27% is something called cold dark matter, invisible to light, detectable only through the gravitational pull it exerts on the galaxies it surrounds, never directly observed in any laboratory on Earth, but demanded by the behavior of nearly every large structure in the cosmos. And 68% is stranger still, a property of empty space itself, a kind of pressure built into the fabric of the universe, pushing space apart at an accelerating rate. Cosmologists call it dark energy. Nobody knows what it actually is. These proportions were not guesses. They were derived from independent measurements that kept agreeing with each other. The temperature fluctuations in the oldest light in the universe, the faint microwave glow that fills all of space, left over from the first 380,000 years of cosmic time, matched the predictions of lambda cold dark matter to extraordinary precision. The way galaxies cluster together across hundreds of millions of light years matched. The way galaxy clusters bend the light of more distant objects matched. The relative abundance of hydrogen and helium forged in the first 3 minutes after the Big Bang matched. Everything pointed in the same direction, and the direction was always lambda cold dark matter. What made the model so powerful was not just that it described the universe's current state, but that it told a coherent story of how the universe arrived at that state. In the first tiny fraction of a second after the Big Bang, matter and energy were distributed almost uniformly across an unimaginably hot, dense plasma. Almost uniformly, but not perfectly. There were tiny ripples in the density of that early fog, regions slightly denser than their surroundings, regions slightly emptier. Gravity got to work on those ripples immediately. Dense regions pulled in more matter. Over millions of years, then hundreds of millions of years, the fog collapsed. The first stars ignited in dense pockets of hydrogen and helium. Those stars gathered into the first dwarf galaxies. And those dwarf galaxies slowly merged and accumulated into larger ones, which merged and accumulated into larger ones still. Small first, large later, always. This prediction, called hierarchical structure formation, was one of the model's most fundamental and most carefully tested conclusions. When the Hubble Space Telescope looked at the deep universe, it found exactly what the model expected. The farther back it looked, the younger and smaller and less organized the galaxies appeared. A galaxy from 2 billion years after the Big Bang looked different from one at 5 billion years. A galaxy at 5 billion years looked different from one at 9 billion. The universe was visibly assembling itself across cosmic time, building complexity out of simplicity in precisely the order the model predicted. Cosmologists had mapped the architecture of cosmic history, and the map matched reality at every scale they could test. There was another dimension to the model's confidence, one less obvious, but equally important: the story of the elements. The universe that emerged from the Big Bang contained almost nothing heavier than hydrogen and helium. Trace amounts of lithium, almost nothing else. Every other element on the periodic table, every atom of oxygen in every ocean, every atom of carbon in every living thing, every atom of iron in every planet's core, was forged later, inside stars, through nuclear fusion, at temperatures of tens of millions of degrees. The first generation of stars lived fast and died violently, seeding space with heavier elements when they exploded as supernovae. A second generation formed from the enriched gas those explosions left behind. Then a third, richer still. Each generation of stellar birth, life, and death made the universe chemically more complex than it had been before. The model described this process in careful detail, and it made a specific prediction about time. Building up a meaningful quantity of oxygen, enough to be detectable in a distant galaxy when a telescope spread its light across wavelengths and looked for chemical fingerprints, required at least 1 billion years of this process. 1 billion years of stars being born, forging oxygen in their cores, dying, and scattering it across space for the next generation to inherit. 1 billion years. That was the chemical minimum. That was the consensus. The Hubble Space Telescope spent decades peering into deep space and found, everywhere it looked, a universe that behaved as expected. The deep fields, long exposures of tiny patches of sky that revealed thousands of galaxies at once, showed a cosmos that grew more primitive the farther back you looked. Young galaxies were small, disorganized, faint. The universe assembled itself gradually, the way a city grows from scattered settlements into something with streets and districts and scale. The story was ordered, it was elegant, it was consistent, and it had been confirmed from so many independent directions, by so many independent instruments, over so many decades, that some researchers genuinely wondered whether the great open questions of cosmology might be answered within their lifetimes. Not all of them, but the framework, they believed, was solid. The foundations were laid. Understand what it means to have that kind of confidence in a scientific model. Lambda, cold dark matter, was not a theory that a few people believed. It was the organizing principle behind billions of dollars of telescope time, behind every major cosmological survey of the previous 2 decades, behind the careers of hundreds of researchers on every continent. Graduate students built dissertations on its predictions. Observatories allocated years of time to test its implications. An entire generation of cosmologists had come of age inside this framework, learned to think with it, learned to see the universe through it. If it was seriously wrong, not incomplete in some minor adjustable way, but structurally wrong in its account of how and when the first structures formed, then research programs would need to be reconsidered. Textbooks would need rewriting. The coherent story of the universe that science had spent 50 years assembling would develop cracks that nobody yet knew how to fill. That was the world the new telescope inherited when it opened its eyes. A field that had earned its confidence. A model that had passed every test. A map that everyone agreed was, if not complete, at least correct in its broad outlines. The images were about to arrive. On the 12th of July, 2022, the President of the United States stood before a screen at the White House and showed the world the first official science image from the new telescope. What appeared on that screen stopped people. A field of galaxies, thousands of them, each one a different shape, spirals and ellipses and smears of distorted light, each one a different color depending on its distance and its age, all of them crowding a patch of sky so small that if you held a grain of sand at arm's length, it would cover the entire region. And every single point of light in that image was not a star. Every point of light was a galaxy. each one containing hundreds of billions of stars of its own. The image reached farther back in time than any photograph ever taken in the history of human observation. Light that had been traveling for billions of years, finally arriving at a mirror 14 meters across, coated in gold, parked 1.5 million kilometers from the planet that built it. Awe is the right word for what people felt. Not excitement, not curiosity. Awe. A specific kind of vertigo that arrives when you understand something viscerally, in your body, rather than just in your mind. The universe is enormous. It is incomprehensibly ancient. You know this. You have been told this. But a moment arrives sometimes when the knowledge becomes something you feel rather than something you hold, and the image on that screen produced it in millions of people simultaneously. Scientists cried. Members of the public stared at their phones and said nothing. Something crossed the gap between what we know and what we can feel, and for a short time, the gap closed. The celebration was real. It deserves to be held here, not used as ironic preamble to the trouble ahead. 30 years of work, $10 billion, 344 mechanical steps that all had to succeed, and they had all succeeded, and the instrument was working, and it was beautiful. That moment was complete in itself. But in research offices at universities across the country and around the world, some astronomers were looking at the same early images with a growing sense that something was not quite right. Garth Illingworth had spent his career at the University of California, Santa Cruz, studying the deep universe. He had looked at more distant galaxies than almost anyone alive. He knew, with a precision that only decades of work can produce, what galaxies at those distances and those ages were supposed to look like. They were supposed to look small, disorganized, faint. The models were clear on this. Hierarchical structure formation meant that the universe at those early epochs should be full of building blocks, not finished buildings. Dwarf galaxies, proto-galaxies, clumps of gas still learning how to hold themselves together. What Illingworth and others were seeing in the early data was not that. Some of the objects looked too large. Some looked too bright. Some showed a degree of structure and organization that the models said should take billions of years to develop. In private conversations among researchers, a word began to circulate. It was a short word, common enough in ordinary usage, carrying very different weight when a scientist uses it about a measurement that does not match a prediction. Wrong. Richard Ellis, a cosmologist at University College London and one of the most respected observational astronomers working, was among the first to say it in a room full of peers. Looking at the early data, he described the presence of these objects as worrying. He called them monsters. That word, too, had a precise meaning in context, and it was not hyperbole. If the measurements held up, if these galaxies were as massive and as distant as they appeared, then they were too large to have formed in the time available to them. They violated the timeline of cosmic history, the way a fully grown tree violates any explanation that says it grew from a seed planted last week. The sample at that point was tiny. The telescope had been returning science data for only a few months. The areas of sky it had examined were small fractions of the total observable universe. And already the images contained objects that strained or exceeded what the model predicted. The statistical logic of that situation was uncomfortable. If anomalies appeared this quickly in a sample this small, then scaling up, surveying the whole sky at those distances, might reveal a universe full of early massive galaxies that lambda-cold dark matter had never anticipated. That possibility was not, at this stage, a conclusion. It was a whisper, a concern among specialists, passed in corridors and emails, not yet in papers. The error bars on early photometric measurements were real and significant. 1 year of data from a new telescope is not enough to overturn 50 years of verified cosmological theory, and no serious researcher was suggesting otherwise. The instruments needed time, the data needed scrutiny, the anomalies needed to be tested, and tested hard before anyone would be entitled to treat them as more than outliers. But the whisper had started, and in February of 2023, it became a paper. The paper landed on the 22nd of February 2023 in the journal Nature. The authors were Ivo Labbé, an astronomer at Swinburne University of Technology in Melbourne, and Erica Nelson at the University of Colorado Boulder, along with a team of colleagues that included Peter van Dokkum at Yale, Joel Leger at Penn State, and Gabriel Brammer. They had been working with the telescope's first early release science data. The earliest observations returned before the instrument had even begun its systematic surveys. And what they had found was difficult to process, even for the people who found it. 6 candidate galaxies, all of them existing between 500 and 700 million years after the Big Bang. And their masses, if the measurements held up, were extraordinary. The standard unit astronomers use when describing the mass of a galaxy is the solar mass, the mass of our own Sun. These 6 candidate galaxies had stellar masses above 10 billion solar masses each. One of them appeared to approach 100 billion solar masses, 100 billion times the mass of our star. That upper figure is roughly comparable to the mass of the present-day Milky Way, the galaxy we live in, which has been building itself for approximately 13 billion years. These candidates had apparently done something comparable in less than a billion. To understand why this matters, you need to hold 2 things in mind at once. The first is what lambda cold dark matter says about that epoch. The model's prediction for galaxies 500 to 700 million years after the Big Bang is explicit. They should be small. They should be the seeds, the building material, the raw components from which larger galaxies will eventually be assembled over billions of years of merging and accretion. The universe at that age is supposed to be full of infant structures, not completed ones. The second thing to hold in mind is the mass involved. The mass of the Milky Way is not a small number that rounds down to 0 if you get the measurements slightly wrong. These candidates, even accounting for significant uncertainty in the estimates, were in a range that the model had simply not predicted for that epoch. Joel Leger, a galaxy evolution researcher at Penn State, who had spent his career working within the framework of the standard model, read the paper and offered a verdict that spread quickly through the community. These objects, he said, were in tension with 99% of cosmological models. He was not saying the models were wrong. He was saying that 99% of them could not account for what the data appeared to show. Erica Nelson, one of the paper's lead authors, put it more directly. "It is just crazy," she said, "that these things seem to exist." That sentence requires a moment. Nelson is a careful scientist working within a rigorous framework. When she uses a word like crazy, she does not mean it loosely. She means that the existence of these objects, if confirmed, sits so far outside the expected parameter space that no comfortable language exists for it. She is describing the sensation of data refusing to fit any box you have built for it. The community responded exactly as it should. The critics arrived, and they brought good arguments. The first line of attack was methodological. The measurements in the Labbé and Nelson paper were photometric, meaning the distances and masses of these galaxies were estimated by analyzing the overall color and brightness of their light across several wavelength bands, rather than by spreading that light into a spectrum and looking for specific chemical signatures. Photometric measurements are inferences. They depend on assumptions about what a galaxy's light should look like at a given distance, what its star formation history was, how much dust it contains. Any of those assumptions could be wrong. And when they are wrong, the error is not random. It tends to push measurements in a consistent direction. Dust is a particular problem. Dust inside a distant galaxy absorbs short wavelength blue light and re-emits it at longer, redder wavelengths. A galaxy heavily loaded with dust can appear significantly more distant and more massive than it actually is, because its light profile resembles that of a much more ancient and red-shifted object. If the 6 candidates were dusty enough, they could be closer, younger, and much less massive than the photometric analysis suggested. A second objection was equally serious. Active galactic nuclei, galaxies whose central supermassive black holes are actively consuming surrounding gas and radiating enormous energy across the electromagnetic spectrum, can outshine the stellar mass of their entire host galaxy by large factors. If any of the 6 candidates contained an undetected active nucleus, its apparent brightness, and therefore its apparent mass, could be dramatically inflated. The galaxy might look like a monster from a distance when it was something far more modest. A third concern was selection. The new telescope was designed to detect the brightest, most luminous objects at the highest redshifts. The brightest objects at any distance are, by definition, the rare extreme end of the distribution. If the instrument was finding monsters, it might be because it could only see monsters, because everything smaller and dimmer was invisible to it at those distances. A census built from outliers is not a census of the population. It is a portrait of the most exceptional members of that population, which can look very different from the average. These were not desperate objections. They were serious scientific arguments made by serious scientific people, and they deserved to be tested rigorously before anyone drew conclusions. The Labbe and Nelson paper acknowledged the uncertainties explicitly. The authors knew the measurements were photometric. They knew the error bars were real. They were not claiming to have overturned the standard model. They were claiming to have found something that demanded follow-up. What made the situation uncomfortable was the arithmetic of what they had found, even taking all the uncertainty into account. There were 6 of them, 6 candidate objects, each individually straining the models, all found in a small early sample before the telescope had even begun its deep systematic programs. The area of sky covered was a fraction of the total observable universe, and already it contained objects that, if real, pointed to something unexpected about how quickly matter could organize itself in the earliest epochs of cosmic history. If these 6 objects were representative of the broader population at those distances, if the whole sky at those redshifts was full of early massive galaxies rather than the building block fragments the model predicted, then what the Labbe and Nelson paper had found was not a measurement error. It was a signal, a quiet, uncertain, unconfirmed signal surrounded by error bars large enough to drive a telescope through, but a signal nonetheless. The field had split along predictable lines. Those who had built careers on lambda cold dark matter pointed at the uncertainties and argued, quite reasonably, that better data would resolve the tension. Those who had been watching the data arrive with gathering unease felt that the pattern was already visible, even in the noise. What both sides agreed on was that the follow-up had to happen. The only way to resolve the question was to take the candidates out of the realm of photometry and into the realm of spectroscopy, to spread the light of these objects across wavelengths and look for the direct chemical fingerprints that would tell you, precisely and without inference, how far away they were and what they were made of. The skeptics had a case. They pressed it hard, and what happened when they were done pressing it was not what anyone on either side had expected. This is how science is supposed to work. A claim arrives that strains the model. The community does not accept it. The community does not dismiss it. The community tests it from every angle it can find, using every tool available, with the explicit intention of proving it wrong if it can be proven wrong. That is not cynicism, it is the mechanism. The health of a scientific framework depends on its willingness to press hard on the things that challenge it. In the months following the Labbe and Nelson paper, the arguments came hard and fast, exactly as they should. Researchers ran the 6 candidate galaxies through independent analyses. They questioned the photometric measurements from multiple directions. They looked for alternative explanations for the anomalous colors and brightnesses. And some of the candidates did not survive the scrutiny. A handful, when examined more carefully with updated calibrations and better dust modeling, came back with revised estimates that were lower, uncomfortably large perhaps, but not catastrophically so, within the range of what the model could accommodate if you squinted at it. The error bars turned out to be real. The skeptics felt vindicated. For a moment, lambda cold dark matter breathed again. But the testing produced something the skeptics had not quite anticipated. To understand what happened next, It helps to understand the difference between the two kinds of measurement that astronomers use to determine how far away a distant galaxy is. Photometric measurement estimates redshift, the degree to which a galaxy's light has been stretched toward the red end of the spectrum by the expansion of the universe, by analyzing the overall color and brightness of the galaxy's light across a series of broad wavelength filters. It is like trying to identify a specific paint color by holding it under different colored lights. You can make a reasonable inference, but you are working with blunt instruments, and the inference depends on assumptions about what you are looking at. Dust, active nuclei, unusual star formation histories, all of them can produce a light profile that resembles something it is not. Spectroscopic measurement is different in kind, not just in degree. Instead of measuring how bright a galaxy looks through several broad filters, spectroscopy spreads the galaxy's light into its individual wavelengths, a detailed map of the entire spectrum from one end to the other. And inside that map, if the instrument is sensitive enough and the exposure is long enough, you can find signatures. Each element in the periodic table produces a specific pattern of bright emission lines and dark absorption lines at known wavelengths when it is heated and when it absorbs radiation. Hydrogen produces its pattern. Oxygen produces its pattern. Carbon, magnesium, silicon, each one a distinct fingerprint. When you find those fingerprints in the spectrum of a distant galaxy, shifted toward longer wavelengths by a measurable amount, you are not estimating. You are measuring. The redshift is precise. The distance is not an inference. It is a calculation from a direct observation. Throughout 2023, spectroscopic follow-up observations were carried out on the candidates that had survived the photometric scrutiny. These were long exposures, demanding significant allocations of telescope time, conducted by multiple independent research teams using different instruments. The results came back one by one. Some of the most alarming early candidates did not survive this stage either. Their spectroscopic redshifts came back lower than the photometric estimates had suggested. They were not as old or as distant as they had appeared. They were large and puzzling, but within the territory where unusual physics might produce an unusual result without requiring the model to be wrong. The skeptical campaign was working, and then the spectroscopic confirmations started coming back for the ones that did survive. The galaxies that passed spectroscopic scrutiny were fewer in number than the original photometric sample, but they were real. Confirmed not by a single observation, not by a single team, but by multiple independent programs pointing the same instruments at the same objects and reading the same fingerprints in the spectrum. These galaxies were as distant as the early measurements had suggested. Some were as massive, and none of the counter-arguments, the dust corrections, the active nucleus contamination hypothesis, the selection bias concern, could explain them away. The specific objects that had resisted every attempt to dismiss them were still there, still anomalous, still sitting in a part of the parameter space where the model said nothing should be. There is an uncomfortable irony in what the skeptical campaign had actually accomplished. By pressing hard on the weakest candidates, it had cleared away the ambiguity. The cases that could be resolved with better data were resolved. What remained was the residue that better data could not touch. The confirmed galaxies were not outliers at the edge of what lambda cold dark matter could accommodate with some effort. They sat in regions where the model's predictions and the observations were not in tension. They were in opposition. Something important needs to be said carefully here, because it is a distinction that popular coverage of this story frequently collapses, and collapsing it makes the situation sound more dramatic than it actually is, while simultaneously making it sound less alarming than it actually is. The confirmed anomalies did not mean that all of lambda cold dark matter was wrong. The model's predictions about the composition of the universe, the proportions of ordinary matter, dark matter, and dark energy remained in excellent agreement with data from many independent sources. The cosmic microwave background, the large-scale clustering of galaxies, the distribution of matter across vast cosmic distances. On all of these questions, lambda cold dark matter continued to perform extraordinarily well. Nobody was suggesting that the universe was not mostly dark energy, or that dark matter did not exist, or that the Big Bang was the wrong starting point. The problem was narrower than that, and narrower problems are, in some ways, harder to fix. The specific failure was in the timeline. How quickly could matter organize itself into large structures in the earliest epochs of cosmic history? Lambda cold dark matter had a clear answer, derived from decades of simulation and observation. The Webb data and that answer were diverging, and a year of careful, disciplined pushback had not resolved the divergence. It had clarified it. The field was no longer arguing about whether there was a problem. It was arguing about how big the problem was. That is a very different conversation, and the instrument was only getting started. The confirmed anomalies from the Labbe and Nelson paper had moved the question from private whisper to open confrontation. The field knew something was wrong with the timeline. What it needed now was not more photometric candidates, but a program systematic enough, deep enough, and precisely measured enough to tell the community how wrong and where. That program had a name. The James Webb Space Telescope Advanced Deep Extragalactic Survey, known within the research community as JADES, was the most ambitious combined imaging and spectroscopic program the telescope would carry out in its early years. The design was simple in concept and staggering in commitment. Point the telescope at two carefully chosen patches of sky and stare. Not for hours, for hundreds of hours. Stare until every photon worth counting had been counted, until the faintest signals had accumulated into measurable data. Kevin Heinlein at the University of Arizona and Stefano Carniani at the Scuola Normale Superiore in Pisa led portions of the analysis, working alongside a large international team. The goal was not to hunt for dramatic objects. The goal was systematic, to build a statistically complete census of the early universe, layer by careful layer, the way a geologist reads rock strata. The survey returned thousands of galaxies. Redshifts confirmed spectroscopically for objects reaching back to within the first few 100 million years of cosmic time. Most of what JADES found was consistent with prior knowledge, filling in gaps, refining measurements, extending the map in the directions the models predicted. The work was precise, careful, and largely confirmatory. Buried inside the catalogue, in a patch of sky in the constellation Fornax, was an object that the team kept checking and rechecking because the data appeared to contain an error. The accumulated evidence from multiple observations, multiple instruments, and multiple independent analyses said the same thing. There was no error. The object was given the designation JADES GSZ 14-0, and the spectroscopic redshift that came back for it was 14.32. That number requires translation before it can be felt. When we describe how far away a distant galaxy is, we use a quantity called redshift, a measure of how much the expansion of the universe has stretched the light traveling toward us since it was emitted. A redshift of 0 would be something right next door. A redshift of 1 is roughly the distance at which light takes about 8 billion years to reach us. A redshift of 14.32 means that the light now arriving at the telescope left its source when the universe was a small fraction of its current age. Specifically, the light left JADES GSZ 14-0290 million years after the Big Bang. The universe, by the best current measurements, is 13.8 billion years old. 290 million years is roughly 2% of that total age. The telescope had found a galaxy that formed at 2% of the age of the universe, but the age was only the beginning of what made this object extraordinary. The galaxy has a radius of 260 parsecs, approximately 850 light-years, giving it a diameter of roughly 1,700 light-years. Compare that to our own Milky Way, which stretches approximately 100,000 light-years from edge to edge. JADES GSZ 14-0 is small. At 290 million years, you would expect it to be small, What you would not expect is for it to be structured, for it to show a coherent, resolved, spatially extended light profile, rather than the indistinct smear of a proto-galactic fragment barely distinguishable from the surrounding intergalactic gas. And yet it was resolved. The telescope could see its shape. It had a shape to see. Its stellar mass, the total mass of all the stars it contained, was approximately 500 million solar masses. By the standards of present-day galaxies, that is modest. By the standards of 290 million years after the Big Bang, it was more than the models of gas collapse and star formation could comfortably explain. Matter does not ignite into stars instantly. The process of gas cooling, collapsing under gravity, fragmenting into individual stellar objects, and converting a meaningful fraction of available mass into stars takes time. And the timescale is not arbitrary. It is governed by physics. And then the spectroscopy revealed oxygen. Oxygen does not form in the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium, and essentially nothing else. Every element heavier than lithium was manufactured later, inside stars, through nuclear fusion reactions at temperatures of tens of millions of degrees. Oxygen specifically is produced in the cores of massive stars, stars several times the mass of our Sun, which fuse lighter elements into oxygen over the course of their lives, then scatter that oxygen across space when they die in supernova explosions. For oxygen to be present in detectable quantities in a galaxy, that galaxy must have already hosted at least one complete generation of stars. Stars that were born from collapsing gas, spent their lifetimes fusing elements in their cores, exhausted their fuel, and exploded. Not one or two stars. Enough stars to enrich the surrounding gas to the point where oxygen signatures are readable in a spectrum. The Standard Model had placed the minimum timescale for that process at roughly 1 billion years. 1 billion years of stellar birth, life, death, and chemical enrichment before a galaxy's spectrum could plausibly show detectable oxygen. Jade's GSZ 14-0 was showing oxygen at 290 million years. Carniani described the difficulty plainly in the team's published work. How, he asked, can nature make such a bright, massive, and large galaxy in less than 300 million years? It was not a rhetorical question. He and his colleagues genuinely did not have an answer. Neither did anyone else in the field. In March of 2025, a second observation confirmed the oxygen detection through an entirely independent method. Using the Atacama Large Millimeter and Submillimeter Array, a network of radio antennas spread across Chile's Atacama Desert at an altitude of 5,000 meters, Carniani, Scaus, and their collaborators detected the specific emission line produced by oxygen directly in the radio portion of the spectrum, confirming the galaxy's distance with a precision far beyond what the original spectroscopic measurement could achieve. The new redshift came back at 14.1793, with an uncertainty smaller than 0.5%. This made it the most distant detection of oxygen ever recorded in the history of astronomy. Let that settle for a moment. The light that confirmed this detection had been traveling for 13.5 billion years. The galaxy itself now sits at a proper distance of approximately 33 billion light-years from Earth, farther away than it was when the light left, because the universe has continued expanding in all the time the light was in transit. We are not looking at something that exists anywhere in the present-day universe. We are looking at a message from a time before the Sun existed, before the Earth existed, before the vast majority of the stars currently visible in the night sky had yet ignited. And that message contained oxygen, which means that somewhere in the window between the Big Bang and this galaxy's 290 million years, an entire generation of stars had to have formed, burned through their lives, and died. Stars that Jades had not yet observed, stars whose own formation would have required the same preconditions: collapsing gas, cooling halos, gravitational seeds, that the Standard Model said should not yet have been in place. The oxygen was not just an anomaly, it was an arrow pointing backward in time, toward a period the telescope had not yet fully seen. What came before Jade's GSZ 14-0? What were the first objects, the real first objects, that seeded the conditions for all of this? That question had no answer. It had barely even been asked before the telescope opened its eyes, because nothing had ever given scientists a reason to ask it with such urgency. And then, weeks after the Jade's confirmation, a second galaxy appeared at the same edge of time, with different properties, and a paper that called it, without apparent irony, a cosmic miracle. The astronomical community had barely begun to absorb the implications of Jade's GSZ 14-0 when Peter Van Dokkum of Yale University and Rohan Naidu of the Massachusetts Institute of Technology announced a separate discovery, an independent observation, a different team, a different object, a different part of the early universe, but the same era and the same impossibility. The galaxy they found sits at a redshift of 14.44. That places it at 280 million years after the Big Bang, 10 million years earlier than Jade's GSZ 14-0. They named it MOMS Z14. The subtitle of their published paper called it, without apparent irony, a cosmic miracle. The word was not chosen carelessly. Van Dokkum and Naidu are careful scientists working in a careful field, and when they reached for that phrase, they were using it in its precise technical sense. Something so statistically improbable under the current theoretical framework that its existence does not merely strain the model, but demands an accounting from it. A result so far outside the predicted distribution that coincidence is not a credible explanation. The galaxy spans approximately 500 light-years across. That is a tiny footprint by any standard in the present-day universe. A fraction of a percent of the Milky Way's diameter, but the span is not the anomaly. At 280 million years, you might expect a galaxy of that size to be a featureless clump. Young stars recently ignited in a loose collection of gas, not yet organized into anything resembling structure. What the spectral data showed instead was a galaxy already undergoing a powerful and organized burst of star formation, converting gas into stars at a rate that, when you account for the galaxy's size, was extraordinary. The universe at that age should not have been capable of driving processes at that rate. One of the most important details in the Van Dokkum and Naidu analysis was what the data did not show. Many early universe objects that look anomalously bright or anomalously massive turn out, on closer inspection, to contain an active galactic nucleus, a supermassive black hole at the galaxy's center that is actively consuming surrounding gas and radiating enormous energy across all wavelengths simultaneously. Active nuclei can outshine the entire stellar content of a galaxy, making it look more massive and more luminous than its stars alone would justify. When astronomers find an object that seems too bright for its age, one of the first questions they ask is whether there is a feeding black hole responsible for the excess light. MOMS Z14 showed no signatures of an active nucleus. The spectrum was clean. The light was coming from stars. This was not a black hole masquerading as a galaxy. It was a galaxy, forging stars at a rate that 280 million years after the Big Bang should not have been physically possible. Then there was the chemistry. The spectral data revealed an elevated ratio of nitrogen to carbon in the galaxy's gas. On its own, that sounds like a small technical detail. In context, it is anything but. In the present-day universe, a high nitrogen to carbon ratio is a signature found specifically in the densest and oldest stellar environments we know of, the globular clusters. These are ancient, tightly packed balls of stars, hundreds of thousands to millions of stars bound together by gravity, orbiting the outer halo of the Milky Way and other large galaxies, most of them formed in the first few 100 million years of cosmic time. Their internal chemistry reflects an intense, compressed history of stellar generations cycling rapidly through birth and death, enriching the gas with specific elemental fingerprints that take a long time to develop. Finding that fingerprint in a galaxy at 280 million years old means MOMS Z14 was not a primitive ancestor of later structure. It was not on its way to becoming something chemically mature. It was already there, already carrying the chemical signature of an environment that in the current universe would tell you you are looking at something ancient. In a universe not yet 300 million years old, it was showing you the chemistry of old age. Here is an analogy that puts the timescale in a different frame. Sharks have existed in Earth's oceans for approximately 450 million years. They were swimming in ancient seas before trees evolved. They survived every mass extinction, including the one that ended the dinosaurs. By any measure of biological time, they are among the most ancient complex creatures we know. MOMS Z14 has existed for 280 million years. This galaxy is younger than sharks, and yet by the model's predictions, it should be in an equivalent of early infancy. A barely structured clump of first-generation stars with nothing resembling the chemical complexity it actually displays. Van Dockum and Naidu and their colleagues were careful in their conclusions. They acknowledged uncertainties. They noted that further observations would be needed to fully characterize the object. They were explicit that the measurements carried error bars and that interpretations built on early data sometimes shift. These are not the hallmarks of researchers overclaiming. These are the hallmarks of researchers who know exactly how extraordinary their finding is and who are determined not to overstate it, because overstatement would make it easier for the rest of the field to dismiss. They still called it a cosmic miracle. 2 galaxies, weeks apart, both at the edge of observable time. Both found before the telescope's most systematic surveys had even properly begun. Both showing properties that the standard model of cosmic structure formation had explicitly predicted would require billions of years to develop. The question that the field had been carefully framing as a possible tension had become something harder to frame that way. And the telescope was still turning, still returning data, still finding things in the early universe that the models had not predicted and that careful scrutiny had not been able to explain away. There was another kind of anomaly accumulating in the survey data, not in what the early universe had built, but in what it had done to the light around it. And this one left no room for inference at all. Every anomaly we have discussed so far has been a version of the same wrongness, something existing that should not yet exist, a galaxy too massive for its age, chemistry too complex for a universe barely 300 million years old, structure where the models predicted only formlessness. But there is another category of wrongness, not the wrongness of something being there when it should not be, but the wrongness of something being visible when it should not be visible, when the light itself should never have reached us. To understand what the telescope found next, you need to understand what the early universe looked like from the inside. After the Big Bang, the cosmos spent the first few 100 million years in a state sometimes called the cosmic dark ages. There were no stars yet. There was no light. There was only a vast, uniform fog of neutral hydrogen gas, hydrogen atoms that had formed when the universe cooled enough, roughly 380,000 years after the Big Bang, for protons and electrons to combine and stop interacting with radiation. From that point forward, the universe was transparent to most forms of light, but it was also dark because nothing was yet generating light to shine through it. Then the first stars ignited. Then the first galaxies formed, and the ultraviolet radiation pouring from those early sources began doing something to the surrounding hydrogen gas, ionizing it, breaking those neutral hydrogen atoms back apart into their component protons and electrons. As more sources switched on and more ionized bubbles grew and merged, the fog began to burn away. Eventually, after hundreds of millions of years of this process, the universe became fully transparent to all forms of radiation. This transition is called rionization. The standard timeline, derived from decades of observation of distant objects and confirmed by measurements of the cosmic microwave background, held that rionization was substantially complete by roughly 1 billion years after the Big Bang. Before that threshold, during the epoch the telescope was now examining, the universe was still mostly opaque, still mostly fog. This matters because of a specific kind of light called Lyman alpha radiation. When hydrogen atoms in a young galaxy absorb ultraviolet photons from hot, newly formed stars, they release energy at a precise ultraviolet wavelength. That wavelength is called Lyman alpha, named for the physicist Theodore Lyman, who first catalogued the series. It is a reliable signature of vigorous star formation. In the present-day universe, where the intergalactic medium is fully ionized and transparent, Lyman alpha photons travel freely across billions of light-years and arrive at our detectors intact. In the early universe, they do not. Neutral hydrogen gas is extraordinarily efficient at absorbing Lyman alpha photons specifically. A photon at that wavelength that enters a region of neutral hydrogen does not pass through. It is captured almost immediately. In a universe that is mostly neutral hydrogen fog, a Lyman alpha signal from a galaxy inside that fog cannot escape. It does not reach us. The Standard Model was explicit on this point. Any Lyman alpha emission from before ionization was effectively erased in transit, not attenuated, erased. With that understood, consider the object designated JADES GSZ 13-1LA. The letters at the end of the designation are not cosmetic. They stand for Lyman alpha. This is a galaxy at a redshift of 13, placing it 330 million years after the Big Bang, well inside the epoch of neutral hydrogen fog. And it is shining in Lyman alpha. Kevin Hainline, one of the researchers on the JADES team at the University of Arizona, put it in the plainest possible terms. "We really should not have found a galaxy like this," he said. That sentence does not sound alarming until you understand precisely what it means. It means that a signal the fog should have absorbed, a signal that the Standard Model said could not travel through the conditions that existed at that moment in cosmic history, has arrived at the telescope. The photons are here. The wavelength has been measured. The identification is not ambiguous. How does this happen? There are two possibilities, and both of them require something to have gone differently than the models predicted. The first possibility is that this galaxy created a bubble around itself, a region of ionized hydrogen large enough that the Lyman alpha photons could travel through it and escape into the wider universe before being absorbed. For a bubble large enough to explain the detection to have existed at 330 million years after the Big Bang, ionizing radiation would have had to begin burning through the neutral hydrogen fog far earlier than the standard timeline allows. The sources driving that ionization, whatever they were, would have had to be active significantly sooner than cosmologists had calculated. The second possibility is that the fog was never as thick as the models assumed, that the neutral hydrogen density in certain regions of the early universe was lower, or patchier, or more variable than the standard account allows, that there were channels of transparency through the fog even before ionization was supposed to have made substantial progress. Either explanation leads to the same conclusion. Ionization began earlier than we thought, and the broader picture from the JADES survey reinforced exactly that. Julian Munoz, an astronomer at the University of Texas at Austin, and his collaborators published a careful accounting in the monthly notices of the Royal Astronomical Society in November of 2024. Their analysis worked from a simple premise. Ionization requires a sufficient number of ionizing photons to split all the neutral hydrogen in the universe. That number can be calculated from the known volume of intergalactic gas. What JADES and other early Webb surveys had revealed was a far greater abundance of bright, energetic, ultraviolet-producing galaxies in the early universe than models had predicted. When Munoz and his team did the accounting, they found that if you took the Webb observations at face value, ionization should have ended 350 to 450 million years earlier than current models place it, at 550 to 650 million years after the Big Bang, rather than the established figure of roughly 1 billion years. Munoz described it as an accounting game. "We know that all hydrogen was neutral before ionization began," he said. "From there, you need enough extreme ultraviolet radiation to split each atom. So at the end of the day, you can do the arithmetic and work out when ionization ended." He was not declaring a crisis. He was not claiming the Standard Model was broken. He was saying, with characteristic precision, that something is missing from the picture. The numbers do not reconcile. That matters. What makes the Lyman alpha detection so significant, what separates it from every other anomaly in this chapter, is that it is not a model-dependent inference. The mass estimates of early galaxies depend on assumptions about dust and star formation history. The Ryanization calculation depends on extrapolations from incomplete surveys. But the Lyman alpha signal leaves no room for that kind of uncertainty. The photons arrived. The wavelength was measured. The signal is what it is. The conclusion follows directly, without inference, without assumption, without the kind of gap that subsequent data can close. A signal the fog should have swallowed got through. The early universe was producing light faster than the models allowed. It was building structure faster than the models allowed. And the number that underlies every measurement in cosmology, the rate at which the universe itself is expanding, was about to give two verified answers that refuse to agree with each other. Every measurement in cosmology rests on a foundation, not a philosophical foundation, a numerical one. A single value from which so much else is derived that if it is wrong, the error propagates upward through every calculation built on top of it, corrupting them quietly in ways that may not become visible until something refuses to match. That value is the Hubble constant. It is named after Edwin Hubble, who in the 1920s made the measurements that confirmed the universe is expanding, that distant galaxies are receding from us, and that the farther away they are, the faster they appear to be moving. The Hubble constant describes the current rate of that expansion. It is expressed in kilometers per second per megaparsec, meaning that for every megaparsec of distance between us and a galaxy, the galaxy is receding from us by that many kilometers every second. A megaparsec is approximately 3.25 million light-years. It is not a unit of everyday scale, but the number itself, whatever it turns out to be, has enormous consequences. If you know how fast the universe is expanding now, you can run the clock backward and calculate when the expansion began, the age of the universe. You can calculate how quickly structures should have assembled in the early cosmos. You can predict the future, whether the expansion will slow, continue at the same pace, or accelerate without limit. The Hubble constant is not just a number, it is the rate of change of everything. For decades, cosmologists argued about its precise value. By the early 2020s, two measurements had emerged as the most credible, and they disagreed. The first method looked backward. The Planck satellite had mapped the cosmic microwave background, the oldest light in the universe, released 380,000 years after the Big Bang, with extraordinary precision. From the pattern of temperature fluctuations in that ancient light, physicists could calculate the early universe's expansion rate and extrapolate forward to the present day. That calculation, built into the Standard Model, yielded a Hubble constant of 67.4 kilometers per second per megaparsec. The second method looked at the nearby universe directly. Adam Rees, a physicist at Johns Hopkins University and a Nobel laureate, led a research collaboration whose name is the supernova H0 for the equation of state of dark energy team, known informally as SH0ES. They built a cosmic distance ladder, a chain of overlapping measurement techniques, each calibrated against the one below it, that allows astronomers to establish the distances to galaxies far enough away that their recession speed is dominated by cosmic expansion rather than by local gravitational motion. The first rung of the ladder used Cepheid variable stars, a class of pulsating stars whose brightness cycles with a period directly related to their true luminosity, making them reliable distance markers. The second rung used Type 1a supernovae, a class of stellar explosion that occurs at a consistent peak luminosity, allowing their apparent brightness to translate directly into distance. The Rees team's measurement, published in 2022, was 73.04 kilometers per second per megaparsec. The gap between the two values is approximately 5 to 6 kilometers per second per megaparsec. In the units being discussed, that sounds like a rounding error. it is not. The statistical significance of the disagreement had reached 5 sigma, the formal threshold in particle physics for claiming a discovery. A 5 sigma result means the probability that the discrepancy is a statistical fluke is less than 1 in 3.5 million. In the context of a disagreement between two measurements of the same physical quantity, 5 sigma is the formal threshold for saying that something is wrong. Not that one measurement is probably slightly off, that something is fundamentally wrong with either the measurements or the model connecting them, or both. There was one prominent hypothesis for where the error might lie: stellar crowding. The Hubble Space Telescope, which Rees and his team had used to observe Cepheid variable stars in distant galaxies, has a finite angular resolution. In galaxies far enough away that individual stars blur together, a Cepheid might appear brighter than it actually is, because nearby stars contribute light to its measured flux. If crowding was systematically inflating the apparent brightness of distant Cepheids, it would inflate the inferred distance to those galaxies, which would inflate the calculated expansion rate, which would explain why the local measurement came in higher than the early universe value. The new telescope was asked to test this. Its resolution is dramatically sharper than the Hubble Space Telescope's, and it observes at infrared wavelengths where dust scattering, another potential source of systematic error, is less severe. If crowding was the explanation, Webb would find it. In February of 2024, Rees published the first set of results. The telescope had observed Cepheid variable stars in 5 galaxies that had also hosted Type 1a supernovae, measuring more than 1,000 individual pulsating stars. The Webb measurements and the Hubble measurements agreed with each other. The Cepheid distances were correct. Crowding was not the explanation. Rees's statement on the findings was precise and direct. With measurement errors negated, he said, "What remains is the real and exciting possibility that we have misunderstood the universe." Later that year, in December of 2024, his team published a more comprehensive analysis, the largest sample of Webb data on this question assembled since the telescope began science operations. The result for all galaxies observed by Webb together with their supernovae was a Hubble constant of 72.6 kilometers per second per megaparsec, nearly identical to the Hubble Space Telescope's value for the same objects. And the possibility that Cepheid crowding was responsible for the discrepancy was ruled out. Not at 5 sigma, but at 8.2 sigma, a threshold more than 50 times more statistically decisive than 5 sigma. Not an edge case, a verdict. Daniel Skolnick of Duke University responded to the full sample findings with characteristic directness. The Hubble tension, he said, is now a Hubble crisis. Consider what that means in its simplest form. 2 independent methods, 2 different physical phenomena used as measuring instruments, 2 sets of data examined, corrected for every known systematic error, verified by 2 different space telescopes operating at different wavelengths. And still, one method gives 67.4 and the other gives 72.6. One universe. 2 answers. This is not a case where one measurement is obviously wrong and needs to be fixed. Both measurements have been examined with extraordinary care. The telescope that provided the most powerful check of the local measurement has confirmed it. The early universe measurement comes from the most precise map of the cosmic microwave background ever produced. Neither is going away. The gap between them is not shrinking. It may be telling us something about physics that we do not yet know. Some process or component in the early or late universe that the standard model does not account for and has never been required to account for, because before this measurement came along, nobody knew it was needed. The field had a name for this. The Hubble tension had been the name for years. That name implied a problem under negotiation, a discrepancy that might yet resolve. The name had changed. What the theorists proposed next was not a resolution. It was a rescue operation. And the rescue operation raised a question that the field has not found a comfortable way to answer. When a scientific model produces a result that disagrees with observation, the scientific community has options. It can reject the observation, It can revise the model, or it can add something to the model, a new ingredient, a new term, a new component that brings the calculation back into agreement with the data. All three responses are legitimate. All three have been used throughout the history of science. The question is not which response to choose, but whether the response you choose is doing real work or merely performing it. The theorists had a proposal for the Hubble crisis. It came from Mark Kamiankowski at Johns Hopkins University and his colleagues, developed in the years leading into the 2020s. It was called early dark energy. The logic of the proposal is straightforward. The Planck satellite measured the cosmic microwave background and derived a Hubble constant of 67.4 kilometers per second per megaparsec. The Rees team measured the local universe and found 73.04. The gap between those two numbers is the crisis. What if something exists, some form of energy, that was briefly present in the very early universe before the cosmic microwave background was released and gave the expansion a brief additional push? If such a burst of energy existed in the first few 100,000 years after the Big Bang, it would shift the Planck-derived Hubble constant upward, toward the value the local measurements produce. The tension dissolves, the model survives. That is the proposal. Now consider what it requires. Early dark energy has never been observed. There is no confirmed measurement of it in any dataset. There is no predicted spectral signature that has been found. There is no laboratory detection, no astronomical fingerprint, no indirect indication of its presence other than the gap it was invented to explain. It is inferred entirely and exclusively from the disagreement between two numbers. In the most precise scientific language available, it is a postulate, an assumption introduced specifically to preserve the consistency of an existing framework in the face of data that does not fit. That alone is not a reason to reject it. Science is full of examples where an unobserved component was proposed to explain anomalous data, searched for, and eventually found. The prediction of the neutrino, proposed decades before any detector could catch one. The prediction of the Higgs boson, postulated to preserve the mathematical consistency of the standard model of particle physics 48 years before its detection at the Large Hadron Collider. Proposing an undetected ingredient is a legitimate scientific move, provided the proposal is specific enough to be tested and falsifiable enough to be disproven. But there is a structural discomfort in the early dark energy proposal that is worth sitting with, and it starts not with what early dark energy is, but with what it joins. Lambda, cold dark matter, the standard model of cosmology, already requires two major undetected ingredients to describe the universe as it is observed. The first is dark matter, an unknown form of matter that makes up 27% of the universe's total mass and energy, detectable only through its gravitational influence on the galaxies it surrounds, undetected in any laboratory on Earth, despite decades of searching at particle colliders and in deep underground detectors designed specifically to find it. The second is dark energy, an unknown property of space itself that makes up 68% of everything, inferred entirely from the fact that the universe's expansion is accelerating, with its physical nature completely unknown and no agreed theory for what it actually is. Add those together and you have 95% of the universe accounted for by things that have never been directly detected. Ordinary matter, atoms, molecules, the substance of every star, every planet, every person, everything anyone has ever seen or measured or touched, makes up the remaining 5%. Now add early dark energy, and the model requires a third invisible, undetected component. Each of these three ingredients is individually defensible. The indirect evidence for dark matter is strong. Galaxy rotation curves, gravitational lensing, structure formation simulations all point to something that behaves as if it were there, even if nobody can put it in a detector. The case for dark energy is real. The acceleration of cosmic expansion is measured, not hypothesized. Early dark energy at least addresses a genuine anomaly. But step back and look at the architecture as a whole. A model that explains the cosmos almost entirely through components that cannot be directly detected or characterized, is a model that is very difficult to falsify. And a model that cannot be falsified is, at some level, a model that cannot be tested. The Kamionkowski proposal is not naive about this. The researchers who developed it are not pretending the epistemological weight does not exist. The field, broadly, is aware of it. But being aware of a problem is not the same as having resolved it. There are other theoretical options. Early dark energy is not the only possible bridge between the two Hubble constant values. A second possibility is that dark energy itself is not constant, that it varies over time rather than maintaining the fixed energy density that the standard model assumes. Data from the Dark Energy Spectroscopic Instrument Survey, published in 2025, provided early hints that dark energy may have weakened since the Big Bang. If confirmed, that would reshape the late universe expansion history and potentially draw the two Hubble constant values closer. A third possibility is more radical still. Perhaps the mathematical assumption underlying every comparison between early universe and late universe measurements, the assumption that the universe is statistically the same in all directions, is not quite right. If the universe has some preferred direction, some large-scale asymmetry, then using an early universe measurement derived under that assumption to predict a present-day measurement could be formally invalid, and the two answers would diverge not because something is wrong with physics, but because the comparison itself is the wrong comparison to make. Each of these possibilities, if confirmed, would require rewriting chapters of cosmology that have been considered closed for decades. As of early 2026, none of them has been confirmed. The honest position in the field is not that the rescue has failed, but that it has not yet succeeded. The anomalies are real, the solutions are proposed, the tests are underway, and the question that sits underneath all of it, the one that the workshops and the papers and the private conversations keep circling back toward without landing on, is the same question it has always been. How many invisible things can one model carry before it stops being an explanation and starts being a catalogue of what we cannot account for? The crisis in the expansion rate was not, it turned out, the end of the anomalies. In the same deep field images that had produced the impossible early galaxies, the Lyman alpha signal, and the Ryanization crisis, a different population of objects had been accumulating in the data since Webb's first light. Nobody had a name for them. Nobody had a category. And for 4 consecutive years, nobody had an explanation. Scattered through the deepest images the telescope had returned since its first light, there were objects that did not fit anything. They appeared as small, compact, intensely red points of light, brighter than they should have been for their apparent size, redder than any known galaxy population, clustered in the first billion years of cosmic history, and then, a billion years later, apparently gone. Hundreds of them, distributed across the survey fields, showing up in program after program. By the time the astronomical community had catalogued them systematically, more than 340 had been documented. The researchers who first noticed them gave them a name that reflected exactly how much they understood. They called them little red dots. No existing category in observational astronomy accounted for them. They were too compact to be ordinary galaxies. They were too bright for their size in ways that resisted simple explanation. Their spectra, the spread of light across wavelengths that allows astronomers to read the composition and behavior of distant objects, showed features that none of the standard templates could reproduce cleanly. They were a genuine observational puzzle, a population of objects the early universe had apparently produced in significant numbers that no physicist had predicted and no model had anticipated. The field began working through hypotheses in the systematic way it always does when confronted with something genuinely new. The first hypothesis, proposed in 2022, was that little red dots were extremely compact starburst galaxies, dense regions undergoing furious star formation at such a rate and in such a confined volume that the ultraviolet emission from young hot stars, redshifted by the expansion of the universe, produced the characteristic red color. It was a reasonable first guess, consistent with the general finding that the early universe was forming stars more vigorously than expected. Spectroscopic analysis refuted it. The spectral signatures did not match what a compact starburst should produce. The hypothesis was dropped. The second hypothesis, which gained traction through 2023 and 2024, was that little red dots were active galactic nuclei, galaxies whose central supermassive black holes were actively consuming surrounding gas and radiating energy across the electromagnetic spectrum. Feeding black holes are powerful X-ray sources. The thermal emission from gas being heated and compressed as it spirals into a black hole produces characteristic X-ray signatures that are detectable across enormous distances. If little red dots were active galactic nuclei, they should be visible in X-ray surveys of the same fields where they appeared in Webb's infrared images. Astronomers checked. Of the hundreds of catalogued little red dots, essentially none were detected in X-rays. 2 out of more than 300. The X-ray hypothesis was effectively refuted. The objects were radiating in ways that active galactic nuclei simply do not. By September of 2025, a third proposal had entered the literature. The idea was that little red dots might be a class of object known theoretically, but never observed. Structures in which a black hole forms the gravitational core of an enormous ball of gas, powering the entire structure from within. The proposal remained unconfirmed. No observation had definitively identified any object as being of this type, and little red dots did not provide clear evidence for it either. The hypothesis was serious enough to be published and discussed, but the field did not converge on it. Then, on the 14th of January, 2026, a paper appeared in Nature from a team at the Niels Bohr Institute's Cosmic Dawn Center at the University of Copenhagen. The authors were Vadim Rusakov, Professor Darach Watson, and their colleagues. They had spent 2 years conducting continuous analysis of the highest quality spectra available from the Webb telescope, applying techniques sensitive enough to detect subtle features in the light that cruder analysis had missed. Their conclusion was specific and testable. The little red dots are young supermassive black holes wrapped in dense cocoons of ionized gas. The mechanism they identified resolved the central mystery that had defeated every previous hypothesis. A black hole at the core of a little red dot is accreting, consuming surrounding material, and generating enormous heat in the process. The radiation it produces travels outward and encounters the dense cocoon. Inside the cocoon, that radiation is scattered and reprocessed by the hot, ionized gas, emerging in a form very different from what a standard active galactic nucleus would produce. The extreme redness comes from this reprocessing, and the missing X-ray emission, the signature that the active galactic nucleus hypothesis predicted and failed to find, is absent because the cocoon absorbs the X-rays before they can escape. They are not missing because the black hole is not there. They are missing because the cocoon is in the way. Watson, one of the principal researchers on the study, described what the finding implies about the object's scale. They are far less massive than people previously believed, he said. The black hole masses in these objects fall between approximately 100,000 and 10 million solar masses, 2 orders of magnitude lower than earlier estimates that had treated the objects as if they were standard active galactic nuclei without a surrounding cocoon. We do not need to invoke completely new types of events to explain them, he said. That is itself a significant statement. The little red dots, under this interpretation, are not a category-breaking impossibility. They are young black holes in an unusual environment, doing something that physics permits, in a configuration that earlier instruments could not resolve. A concurrent paper from researchers at the Harvard-Smithsonian Center for Astrophysics proposed a different angle on the same population. Their analysis focused not on what the objects are, but on how they form. Specifically, that little red dots may arise naturally in dark matter halos with very low angular momentum. Halos that spin slowly would collapse differently from their faster rotating counterparts, producing extremely compact, dense structures. That formation mechanism, the researchers argued, could explain the object's characteristic compactness and their abundance in the early universe without requiring unusual physics. The two papers are not strictly contradictory. One addresses what the objects are. The other addresses how the conditions for their formation arise. The field is still processing both. What the Copenhagen paper most importantly provides is a resolution to the 4-year sequence of wrong answers. The little red dots are not a population without explanation. They have a leading explanation now, one that is peer-reviewed, published in Nature, consistent with the spectroscopic data, and free of the objections that defeated the previous hypotheses. That is not the same as settled, but it is the closest the field has come. Scale the finding up, and the implication is striking. Hundreds of these objects were found in a small fraction of the survey area. If the cocoon-wrapped young black hole interpretation holds, the early universe was seeded with rapidly growing black holes at a density and at an epoch that the standard model did not predict. The formation of the first supermassive black holes, a problem cosmology has grappled with for decades, may have proceeded through a phase that no one observed directly until this telescope came along and produced light that previous instruments could not read. 4 years of wrong answers. One paper that may be the right one. And while astronomers were cataloguing objects they could not name, a quieter finding was accumulating in the same survey data. One that, if confirmed, would not add another anomaly to the list, but call into question the mathematical foundation beneath all of the lists simultaneously. Every calculation in modern cosmology rests on an assumption so fundamental that most textbooks do not present it as an assumption at all. It is presented as a starting condition, a feature of reality that makes the mathematics tractable. The assumption is this: the universe, at large enough scales, is the same everywhere and in every direction. It has no preferred location. It has no preferred axis. Viewed from far enough away, it has no handedness, no distinguishable difference between left and right, between one orientation and its mirror image. This is the cosmological principle, and it is not merely a philosophical position. It is the mathematical foundation beneath the standard model. The equations that describe cosmic expansion, structure formation, and the relationship between the early and late universe are derived under this assumption. Remove it, and the equations no longer apply in the way they have been applied. Every inference drawn from those equations, the age of the universe, the composition of its contents, the timeline of its history, becomes contingent on a foundation that has not been verified, only assumed. In 2025, a paper appeared in the monthly notices of the Royal Astronomical Society that posed a quiet but serious challenge to that assumption. Leo Shamir is an associate professor of computer science at Kansas State University. His research applies computational analysis to large-scale astronomical data sets, looking for statistical patterns in populations of objects too numerous to be examined individually. He turned his methods to the question of galaxy spin directions. Specifically, the question of whether spiral galaxies in the early universe rotate preferentially in one direction or the other. In a universe that obeys the cosmological principle, the answer should be straightforward. Galaxies can rotate either clockwise or counterclockwise, depending on how their constituent matter happened to collapse and acquire angular momentum during formation. There is no physical mechanism in the standard model that would give the universe a preferred rotation direction, so the distribution of spin orientations should be essentially random. Statistically, roughly half of all galaxies rotating one way and half the other, a ratio of approximately 1:1. Shamir analyzed the spin directions of spiral galaxies in the JADE survey, the same deep field program that had produced JADE's GSZ 14-0 and the Lyman alpha detection. Among 263 galaxies, whose rotation direction could be determined by the geometry of their spiral arms, approximately 2/3 were rotating clockwise. Roughly 1/3 were counterclockwise. The probability of this asymmetry arising by chance, under the assumption of a randomly distributed population, was less than 1%, 2:1. In a universe where the expected ratio is 1:1. Before drawing any conclusion from this, it is necessary to hold both explanations that Shamir himself identifies in mind simultaneously. because the finding is only meaningful if you understand that one of them would require nothing unusual at all. The cosmological explanation is the one that gets the attention. If the asymmetry is real and reflects the large-scale structure of the universe, it means the cosmos inherited a directional bias from the moment of its origin. The Big Bang, in this reading, was not perfectly symmetric. The universe was born with a preferred orientation, an asymmetry in its initial conditions that encoded itself in the rotation of the first structures to form. Those structures passed the asymmetry down through billions of years of merging and accretion, and it is still readable today in the spin directions of ancient spiral galaxies. The cosmological principle, the assumption of isotropy, of no preferred direction, would be violated, and every calculation built on that assumption would need to be revisited. The mundane explanation is equally important, and Shamir discusses it directly. The Milky Way, the galaxy we live in, is rotating. As it rotates, it carries the Earth and every observatory on it with it. Because of the Doppler shift effect, a galaxy rotating in the opposite direction to the Milky Way, relative to our line of sight, will appear slightly brighter to us than a galaxy rotating in the same direction. Slightly brighter means slightly more likely to be detected and catalogued in a survey limited by sensitivity. This effect, if real, would produce an apparent asymmetry in the catalogued population that has nothing to do with the large-scale structure of the universe and everything to do with where we happen to be standing and which direction we happen to be moving. It would be a measurement artifact, not a physical phenomenon. These two explanations lead to completely different conclusions. The first would be one of the most consequential discoveries in the history of cosmology. The second would be a technical correction to a catalogue analysis. The data, at this sample size, cannot tell them apart. 263 classified galaxies is not a large sample for an effect that would need to be demonstrated across millions of objects to be considered robust. The JADE survey covers a small patch of sky, and the statistical behavior of small samples can be misleading in ways that disappear at scale. Systematic errors in automatically determining spiral galaxy rotation directions at cosmological distances are real and not trivial. The orientation of spiral arms becomes ambiguous at certain viewing angles and certain redshifts, and an algorithm that errs in one direction at those ambiguous cases can introduce exactly the kind of apparent asymmetry Shamir found. These concerns have been raised by other researchers in the field, and they are legitimate. The finding is being taken seriously. It has not been confirmed. It has not been refuted. It is at the stage where a measurement has been made, a result obtained, a methodology published, and the community is waiting for independent verification at larger scale before deciding what it means. But the reason it belongs in this account, alongside the impossible early galaxies, the Hubble tension, the Lyman alpha signal, and the little red dots, is what it would mean if it holds. Every other anomaly in this story challenges a specific prediction of lambda cold dark matter. The galaxy rotation asymmetry, if confirmed, does not challenge a prediction. It challenges the premise. It asks whether the foundation on which every prediction of the standard model rests, the assumption that the universe has no preferred direction, is actually true. A model tested against data is only as reliable as the assumptions that connect the model to the measurement. If one of those assumptions has never been directly verified, the tests themselves carry an uncertainty that was invisible until someone thought to look. Shamir looked. The field is watching. Before James Webb launched, mainstream cosmology had a settled response to the kinds of questions the telescope was now raising. None of the anomalies would appear because the model did not predict them. There was, however, one theoretical framework that had been predicting some of them for more than 40 years, and the field had spent 40 years not listening. The problem that Mordechai Milgram was trying to solve in the early 1980s was not exotic. It was embarrassingly practical. Galaxies rotate at speeds that should tear them apart. If you measure the mass of a spiral galaxy, the mass you can directly observe, meaning the stars and gas and dust that emit or absorb light, and you calculate how fast the outer regions of that galaxy should be orbiting around its center given that observed mass, you get a number. And when you look at how fast those outer regions are actually moving, you get a larger number. The discrepancy is not marginal. The outer arms of a galaxy like our own Milky Way move at roughly the same speed as the inner regions, when Newton's law of gravity predicts they should be moving much slower. If you remove the additional mass that the orbital speeds imply must be present, the outer regions should be flying off into intergalactic space. They are not. Something is holding them in. The mainstream answer to this problem, the answer that became a foundational assumption of lambda cold dark matter, was dark matter, an invisible form of mass that surrounds galaxies in vast halos, contributing gravitational pull that the visible matter cannot supply, keeping the outer arms in their orbits without betraying its presence by emitting or absorbing any light. The dark matter answer made the problem tractable. It was incorporated into the Standard Model. It became the assumed truth. Milgram, a physicist at the Weizmann Institute of Science in Israel, looked at the same problem and asked a different question. What if the discrepancy was not about matter at all? What if it was about gravity? In 1983, he published 3 consecutive papers in the Astrophysical Journal, laying out the complete framework of what he called modified Newtonian dynamics. The core proposal was this: at very low accelerations far below anything experienced anywhere in the solar system, far below anything that had ever been tested in a laboratory, gravity does not behave the way Newton's law describes. In the regime of very weak gravitational fields, the law is different. It falls off more slowly with distance than the standard inverse square relationship predicts. The result is that in the outer reaches of a galaxy, where stars and gas clouds are moving under very low acceleration, the gravitational force is stronger than Newton's law would calculate, strong enough to keep those outer regions in orbit, without any dark matter required. The framework made specific predictions. It predicted the relationship between a galaxy's mass and the flat plateau speed of its outer rotation curve, a relationship called the Tully-Fisher relation. It predicted which galaxies would show large mass discrepancies and which would show small ones. In galaxy after galaxy, the predictions matched the observations with a precision that dark matter models, for all their success at larger scales, struggled to reproduce at the level of individual galaxy structure. For the next 4 decades, mainstream cosmology largely ignored it. Lambda cold dark matter was performing too well on the tests that mattered most: the cosmic microwave background, the clustering of galaxies at large scales, the observed distribution of galaxy clusters, the abundances of light elements from the first 3 minutes after the Big Bang. On all of these, the Standard Model produced answers that matched the data with extraordinary precision. Modified Newtonian dynamics could explain galaxy rotation curves, but had no clear extension to those larger-scale phenomena. At the scale of galaxy clusters, it struggled to account for the observed dynamics without invoking some form of additional mass. It had not produced a fully relativistic theory, a version of the framework that could make precise predictions about gravitational lensing and the cosmic microwave background at the level of precision that Planck and Hubble and subsequent surveys could test. The field made a collective judgment. Modified Newtonian dynamics was interesting. It was not important. Funding went elsewhere. The major conference programs did not feature it prominently. Graduate students working on it were advised, sometimes gently and sometimes not, that their career prospects were better spent on questions within the mainstream framework. The theory survived because a small, persistent community kept refining it, kept testing its predictions against new data, and kept finding that at galactic scales, it kept working. But survival at the margins is not the same as being taken seriously at the center. James Webb changed the calculation. The galaxy formation anomalies are problems for a dark matter framework. Lambda cold dark matter's hierarchical formation scenario, driven by cold dark matter accumulating in gravitational halos, makes specific predictions about how quickly large structures can form. Those predictions are in tension with what the telescope is finding. Modified Newtonian dynamics, by contrast, predict some aspects of early structure formation differently, and some of those predictions are more consistent with the Webb data. The Ryanization timeline crisis arises in part because the telescope is finding more compact, efficient star-forming galaxies than dark matter simulations produce. Modified Newtonian dynamics, operating without the dark matter scaffolding, allows for different modes of gravitational collapse that can in some cases produce more efficient early structure. This does not mean modified Newtonian dynamics is correct. Its unresolved problems are real, and the researchers who work on it acknowledge them honestly. Galaxy clusters remain a challenge. The observed dynamics of cluster mergers and the way cluster gas behaves still seem to require something beyond what the basic framework provides. The absence of a complete relativistic formulation limits the precision with which it can be tested against some of the most powerful cosmological data sets. There are observations it cannot explain as cleanly as its proponents would like, and the field is right to hold those objections in mind. But a framework that spent 40 years in the scientific wilderness is now, undeniably, back at the table. Researchers who were once told they were working on a dead end are being invited to contribute to analyses of Webb data. Their predictions are being tested with genuine openness. That change is real, and it raises a question that the field does not have a comfortable answer to. What does it mean when an idea that was marginalized for 4 decades turns out to have been pointing towards something real? It means the mainstream was wrong to dismiss it. It means the mechanisms that science uses to allocate attention and resources, the grant committees, the hiring panels, the journal editors, the prestige hierarchies that determine whose work gets read and whose gets filed, failed. For 40 years, in one of the most consequential theoretical questions in cosmology, those mechanisms directed resources away from something worth investigating, and the investigation happened anyway, carried forward by people working at the edges with limited support. The ideas survived because they were right about something. That is the part worth holding on to. Modified Newtonian dynamics waited 40 years for data that would force the center of the field to pay attention. The question now is whether this moment, the accumulation of Webb anomalies pressing against the standard model from multiple directions simultaneously, resembles other moments in the history of science when great frameworks did not just absorb the pressure, but finally broke under it, because they have broken before. And the pattern, when you look at it carefully, is not what most people expect. Great theories do not fall the way most people imagine they do. Popular mythology has a single devastating experiment, a crucial observation that arrives like a hammer and shatters the old certainty in an afternoon. It almost never works that way. What actually happens is slower, stranger, and in some respects, more unsettling. Anomalies accumulate. The defenders of the framework explain each one, usually convincingly. They find corrections, alternative interpretations, sources of systematic error that might account for the discrepancy. The framework adapts, it acquires patches, it endures. And then, at some point that is hard to identify precisely as it happens, the weight of unexplained observations reaches a threshold that no patch can address, and the framework begins to change into something different from what it was. Not overnight. Slowly, then suddenly. Consider what happened to Newtonian gravity. At the time of its dominance, it was the most successful scientific theory in human history. Isaac Newton's law of universal gravitation predicted the orbits of the planets with extraordinary precision, explained the tides, gave engineers the tools to design machines that launched the industrial age, and remained unchallenged for more than 200 years. It had passed every test ever put to it. The confidence in Newtonian mechanics among educated people in the 19th century was not faith, it was earned. Every prediction had come back confirmed. Then, astronomers looked carefully at Mercury. The orbit of Mercury, the innermost planet, does not close perfectly on itself. It precesses. The axis of its elliptical path rotates slowly over time, tracing a rosette pattern rather than a simple closed loop. Newton's law predicted this precession. The observed precession was larger. The discrepancy between the predicted and measured value was 43 arcseconds per century. 43 arcseconds is a tiny angle, roughly 1/100th of a degree, across 365 days. In practical terms, it is invisible. In the terms of 19th century precision astronomy, it was unmistakable and repeatable and undeniable. For decades, astronomers and mathematicians proposed explanations. Perhaps there was an unseen planet, they called it Vulcan, interior to Mercury's orbit, contributing additional gravitational influence that the calculations were missing. No such planet was ever found. Perhaps the Sun was slightly oblate, its mass distribution marginally non-uniform in a way that would shift the precession. Measurements ruled it out. Every proposed explanation either failed observationally or introduced new problems elsewhere. The anomaly would not go away. It took 40 years of discomfort with a number that would not resolve, before Einstein's general theory of relativity arrived and derived precisely that precession rate from first principles, without any additional assumptions, as a natural consequence of the geometry of curved space-time around a massive body. Newtonian gravity had not been wrong exactly. It had been an approximation that was excellent in most regimes and insufficient in one specific case, where the gravitational field was strong and the accuracy required was extreme. General relativity subsumed it, but the anomaly existed for 4 decades before the framework arrived to account for it. The static universe fell differently. Before Edwin Hubble published his measurements of galactic redshifts in the 1920s, the dominant cosmological assumption was that the universe existed in a permanent, unchanging, steady state. It had always existed. It would always exist. The stars and galaxies were fixed, on average, in a stable configuration. Einstein himself had been so committed to this assumption that when his own field equations of general relativity implied a dynamic, expanding universe, he introduced an additional term, the cosmological constant, specifically to cancel the expansion and produce a static solution. He later called it the greatest blunder of his career. Hubble published, "The galaxies were receding. The universe was expanding. The static model did not yield gradually. It was gone almost immediately. The evidence was direct, the implication was unambiguous, and the alternative was so clearly superior that resistance collapsed within years rather than decades." The steady-state model of the 20th century fell somewhere between those two cases. Through the 1940s and 1950s, the astronomer Fred Hoyle and his colleagues argued that the universe had no beginning and no end, that matter was continuously created in the spaces between galaxies at exactly the rate required to maintain a constant average density as space expanded. The model had genuine predictive power and an appealing mathematical elegance. Hoyle was a formidable scientist and a formidable defender of the idea. The debate was real and serious for the better part of 2 decades. In 1965, Arno Penzias and Robert Wilson detected the cosmic microwave background, a faint, uniform glow of microwave radiation filling all of space equally in every direction, with a temperature of approximately 2.7 degrees above absolute zero. There was no mechanism in the steady-state model for this radiation to exist. In the hot Big Bang model, it was a direct and specific prediction, the cooled remnant of the intense radiation that had filled the universe when it was young, dense, and opaque. The detection was not a single piece of evidence in an ongoing debate. It was, in the context of the theories in competition, decisive. The steady-state model had nowhere to go. Lambda cold dark matter has a history with anomalies. The missing satellites problem, the observation that the standard model predicted far more small satellite galaxies around the Milky Way than astronomers could find, was a serious challenge for years and was substantially resolved through better modeling of how baryonic physics suppresses star formation in small halos. The too big to fail problem, a related tension between simulated and observed dwarf galaxies, was similarly addressed. The model has shown a remarkable capacity to absorb challenges through refinement rather than replacement, and this track record is not nothing. It is the basis for the majority position among working cosmologists that lambda cold dark matter will survive. But the rate of anomalies arriving from the new telescope is different in character from anything the field has processed in recent decades. In fewer than 3 years of scientific operation, the telescope produced more significant challenges to the standard model than the previous decade of combined observations had generated. And the anomalies are not of a single type that might trace back to a single missing ingredient. They span galaxy formation timing, chemical evolution, the expansion rate, the reionization timeline, and potentially the large-scale symmetry of the universe itself. They arrive from different instruments, different research teams, different methodologies, all pointing at related problems from different directions. The honest state of the field in early 2026, as best as can be discerned from the conference proceedings and the papers and the private conversations of working cosmologists, is not confident. It is distributed. One group, probably still the majority, believes the standard model will survive this period through improved simulations and better treatment of the complex processes. Star formation feedback, gas dynamics, the interaction of radiation with matter, that the current generation of models handles imperfectly. The anomalies, in this view, reflect computational limitations rather than theoretical failures. A second group believes that the current challenges require fundamental revision to the model's core assumptions, not just parameter adjustments or better physics engines. A third group, smaller but growing in recent years, reaches for a word that mainstream cosmology has historically resisted: paradigm shift. What is perhaps most telling is the proportion of working cosmologists who, asked privately, which group is right, say they do not know. At a workshop in 2024, a senior researcher characterized the situation with the kind of directness that tends to emerge in private rather than in print. "The data is telling us something," he said. "We don't agree on what. History says the model will probably survive. History also says that when anomalies are varied enough, consistent enough, and sufficiently resistant to individual explanation, the model that survives does so as something recognizably different from what it was when the pressure began." The question is not whether lambda cold dark matter will change. The question is how much. And the instrument that will most directly determine the answer is already built. There is a fundamental limitation built into everything the new telescope has shown us, and it is important to name it clearly before drawing conclusions from it. The James Webb Space Telescope is not a survey instrument. It is a precision instrument. It looks at extraordinarily small patches of sky with extraordinary depth and sensitivity. The field of view of its primary camera covers a patch of sky comparable to a grain of sand held at arm's length. The galaxies it has examined in detail are drawn from a tiny, tiny fraction of the observable universe. That limitation cuts two ways simultaneously. On one hand, it means the anomalies are real discoveries. Finding impossible early galaxies, an unexplained Lyman alpha signal, and objects that defeated 4 years of classification attempts, all within those postage stamp fields, is remarkable precisely because the sample is so small. If the anomalies are genuine features of the early universe and not local peculiarities of the specific regions the telescope examined, then scaling up to the full sky should reveal vastly more of them. The telescope has been looking at a few grains of sand on a beach and finding things that should not be there. If those things are real, the beach is full of them. On the other hand, there is a version of the story in which the anomalies are statistical outliers, the result of having examined a few especially unusual regions of a vast cosmos, and having mistaken the exceptional for the representative. The early galaxy problem, the reionization tension, the expansion rate disagreement, each of these could, in principle, be resolved or substantially modified if a much larger survey found that the fields Webb examined were atypically dense, atypically bright, or atypically active. That is not the most likely explanation for the weight of evidence accumulated so far, but it cannot be ruled out on the basis of what a few small deep fields have returned. The next instrument is designed to resolve this ambiguity entirely, and it is already built. The Nancy Grace Roman Space Telescope completed its full assembly on the 25th of November, 2025, at the Goddard Space Flight Center in Maryland. It is committed to launch no later than May of 2027. Teams are working toward a launch as early as autumn of 2026. A Falcon Heavy rocket will carry it to a position approximately 1.5 million kilometers from Earth, in the same region of gravitational stability the Webb telescope occupies. Roman carries a primary mirror 2.4 meters across, the same diameter as the Hubble Space Telescope's mirror. But its wide-field instrument produces a field of view at least 100 times larger than Hubble's per single pointing. Where the Webb telescope sees a postage stamp, Roman sees a poster. Where Webb can examine a few thousand galaxies in a deep field over hundreds of hours of exposure time, Roman will survey hundreds of millions of galaxies across cosmic time, accumulating statistics that no previous instrument has been able to approach. The telescope has three primary methods for addressing the questions that the Webb anomalies have raised most sharply. The first method uses baryon acoustic oscillations. In the very early universe, sound waves propagated through the hot plasma of the Big Bang, imprinting a characteristic scale on the distribution of matter, a preferred separation distance that is still visible today in the clustering of galaxies across hundreds of millions of light years. By measuring that scale precisely at many different epochs of cosmic history, Roman can map how the expansion rate has changed over time. If the Hubble tension reflects a genuine difference between early and late universe physics, that map will show it. The second method uses Type 1a supernovae. These stellar explosions occur at a consistent peak brightness, allowing astronomers to measure their distances from their apparent faintness. The survey that first revealed the accelerating expansion of the universe used this technique with a sample of dozens of supernovae. Roman will find and characterize hundreds of thousands of them across a vastly greater range of cosmic distances. The statistical power of that sample will either confirm the current picture of dark energy or reveal how it has changed across cosmic time with a precision that no previous survey could achieve. The third method uses weak gravitational lensing, the subtle distortion of background galaxy images by the gravitational influence of matter in the foreground. By measuring these distortions across enormous numbers of galaxies, Roman can map the distribution of dark matter across the observable universe and track how that distribution has evolved over billions of years. The evolution of cosmic structure encoded in those maps will either match what lambda-cold dark matter predicts, or show where and by how much it departs from it. Together, those three methods make Roman, in the specific context of everything the Webb telescope has raised, something more than a powerful observatory. They make it a verdict machine. If the Webb anomalies are real features of the early universe, if the early galaxy population is genuinely overmassive, if the expansion rate genuinely gives two incompatible answers, if the structure of the cosmos is genuinely more complex and more asymmetric than the standard model allows, Roman surveys will make those findings statistically undeniable at a scale that no skeptical argument about small sample sizes can address. And if the anomalies are the products of sampling bias, of having looked at unusual patches of sky and drawn premature conclusions, that truth will be equally undeniable. The telescope is named for Nancy Grace Roman, who died in 2018. She was the first chief of astronomy at the National Aeronautics and Space Administration, known as NASA, and spent much of her career arguing for a particular philosophy of space-based observation, that broad surveys of large areas of sky would return more fundamental knowledge about the universe than narrow, deep observations of small fields. The major surveys of the cosmos, from the Hubble Space Telescope's observations of thousands of galaxies across deep fields to the statistical programs that mapped the large-scale structure of the universe, owe their existence in part to the institutional advocacy she conducted over decades, often against significant resistance. It is a philosophy that is now embedded in the telescope that bears her name. James Webb found the questions. Roman is being built to find out how seriously to take them. When its first wide-field surveys return data, the distribution of opinion inside cosmology will face a test that no amount of individual interpretation can manage. The numbers will either hold up at scale or they will not. And the universe, which has never adjusted its behavior to match anyone's preferred outcome, will continue being whatever it has always been, waiting for better instruments to catch it more precisely. The instrument is ready. The questions are waiting. Go back to the beginning. Christmas morning, 2021. A rocket rising from a launch facility carved out of jungle on the northeastern coast of South America, carrying inside its nose cone 18 gold-coated hexagons folded against 2 side panels, waiting to become something. Engineers in control rooms in Baltimore and Paris, and across 2 continents who had spent in some cases the better part of their working lives making that morning possible, sat with their hands in their laps and their eyes on screens. Nobody cheered. The people who understood what was at stake were too frightened to celebrate. The universe had not been consulted about any of this. It had not adjusted itself in anticipation of what the telescope would find. It was simply what it had always been, and it was about to show us. 3 years later, here is what it has sent home. A galaxy formed 290 million years after the Big Bang, containing oxygen, an element that should have taken at least 1 billion years to synthesize, confirmed by independent observation from radio antennas in the Atacama Desert as the most distant detection of oxygen ever recorded. A second galaxy, at 280 million years, chemically mature in ways that required billions of years to develop, already showing the fingerprint of environments that in the present-day universe are among the oldest things we know. A Lyman alpha signal from a galaxy 330 million years old, shining through fog that should have swallowed it completely, carrying the implication that the universe's transition from opaque to transparent happened hundreds of millions of years earlier than every previous timeline placed it. A Hubble constant that measures one value when you look backward through the oldest light in the universe, and a different value when you look at the nearby cosmos with the most precise instruments ever built, and the gap between them confirmed at 8.2 sigma after every plausible source of error has been ruled out. Hundreds of compact red objects in the first billion years of cosmic history that defeated 4 years of classification, now with a compelling leading explanation that no one predicted. Young supermassive black holes wrapped in gas cocoons, seeding the structure that would follow. A suggestion in the spin directions of ancient spiral galaxies that the universe may have been born with a preferred orientation. Still unconfirmed, still contested, still pointing toward a question nobody had thought to ask this precisely before. And a theoretical framework that spent 40 years marginalized, kept alive at the edges of the field by people told they were wasting their time, now back at the table because the data from a $10 billion telescope is producing anomalies that the framework predicted and the mainstream did not. This is what we know. The universe built structure faster than lambda cold dark matter predicted. The expansion rate does not give a single consistent answer, even when the measurements are verified and the errors are ruled out. The Ryanization timeline is in tension with the models by hundreds of millions of years in the most sensitive and consequential window of cosmic history. Objects exist, confirmed, spectroscopically verified, impossible to dismiss, for which our current formation models do not have a complete account. These are not edge cases or rounding errors. They are patterns arriving from different instruments, different teams, different methodologies, pointing at the same set of unresolved problems from different directions. This is what we do not know. What came before the galaxy that was making oxygen at 290 million years? What generated the first generation of stars whose deaths made that oxygen possible? What dark matter actually is, if it exists at all in the form the standard model requires? What dark energy is? Why the 2 Hubble constant measurements disagree with each other? Whether the galaxy rotation asymmetry reflects something encoded in the universe at the moment of the Big Bang, or a mundane effect of our position inside a rotating galaxy. Whether lambda cold dark matter needs to be adjusted in specific ways, or whether the adjustments, accumulated, will eventually require something that no longer resembles the model they were meant to preserve. None of those questions have answers. All of them are live. And somewhere in the middle of all of this, in the data and the papers and the conference presentations and the careful, measured language of researchers doing their best to say precisely what the evidence does and does not support. There is a human cost that the language of science does not easily express. Alison Kirkpatrick is a professor of astronomy at the University of Kansas. She built her research program on lambda cold dark matter. She learned the framework in graduate school, taught it to her own students, published papers that elaborated its predictions, built the professional infrastructure of her career on its assumptions. In 2023, she said this: "Right now, I find myself lying awake at 3 o'clock in the morning, wondering if everything I've ever done is wrong." That sentence lands differently for scientists than it does for everyone else. For anyone who has not spent 10 or 15 years constructing a professional identity inside a particular framework, learning to think with it, learning to see the universe through it, staking your reputation on questions it generated, and your methodology on tools it provided, it sounds like anxiety. For anyone who has, it sounds like something closer to grief. The loss of a map you trusted. The disorientation of discovering that the territory may be different from what you were trained to expect. Kirkpatrick has not stopped working. She is still at her desk, still analyzing data, still contributing to a field that is, in its best moments, collectively honest about the limits of what it knows. The grief is real, and the exhilaration is real, and they coexist. If the map is wrong, the territory is more interesting than anyone knew. The career you thought you had, confirming and extending a mostly complete picture of how the universe works, turns out to be something more open, more uncertain, and more alive than that. It is frightening. It is also extraordinary. That is science working exactly as it should, producing data that challenges assumptions, forcing revision, creating the productive disorientation that precedes genuine understanding. Every researcher in this story who cannot sleep because the numbers will not resolve, every graduate student who chose a dissertation topic based on what Webb would find and is now sitting with data their models did not predict, every theorist whose favorite explanation survived every previous challenge and is now being pressed from 5 directions at once, they are all at the center of one of the most significant moments in the history of this science, whether they asked to be or not. There is one more thing to say, and it is the most personal thing. Every atom of oxygen in your lungs was forged inside a star that exploded before our solar system formed. Every atom of iron in your blood was manufactured in the nuclear furnace of a massive star that lived its entire life and died violently before the sun ignited. The carbon in your bones, the calcium in your teeth, the nitrogen in your DNA, all of it assembled in stellar interiors across billions of years of cosmic history, scattered across space, incorporated into the cloud that became our star and our planets, incorporated eventually into you. You are not a passive observer of the universe. You are made of it, out of the very processes the telescope was built to understand. The telescope was built to answer questions about where all of that came from, about the first structures, the first light, the first chemistry. What it found was not confirmation. It found complication, productive, scientifically rich, intellectually transformative complication that has moved the questions somewhere better than where they started. The map we had was good. It may not be good enough. What comes next will be built by the people who cannot look away from the numbers that will not resolve, working with instruments that can see what no instrument before them could reach. One of those instruments is already assembled, waiting for its rocket. Another is still up there, parked 1.5 million kilometers from the planet that built it, cooling itself to within 7 degrees of absolute zero, aimed at the oldest darkness in existence. The universe does not wait for its models to catch up. It never has. For 13.8 billion years, it has been what it is, indifferent to every framework constructed to describe it, continuing to evolve and expand and structure itself according to rules the most powerful observatory ever launched is only now beginning to read clearly. The best questions in the history of this science are open. Every one of them is live, and somewhere in the dark, a gold mirror keeps turning.